Welcome to The Explainer. Today we're looking at something you probably use literally every single day, but, rarely stop to actually think about. A map isn't just a simple picture of the ground. Not even close. Instead, we're going to look at traditional and digital cartography for what it truly is, a cutting-edge process of programming a visual interface for the physical world. Think of it as a complex software stack. It's where chaotic, infinite real-world data is compiled, encrypted, and then rendered into a sleek, incredibly intuitive user interface that your brain can process in milliseconds. It's a fascinating translation from reality to design, and today we're going to decode exactly how the whole shebang happens. Okay, let's dive into this. On the left is something you rely on constantly, a mobile navigation app, and on the right, a thematic election map. Now, both of these are doing something absolutely incredible. They are acting as interfaces. The navigation map is actively stripping away all the overwhelming complexity of a physical city, the textures of the buildings, the weather, the noise, and it's giving you only the exact geospatial modeling you need to get from point A to point B. The election map does the exact same thing, but for statistical data, mapping things like valid and invalid votes directly to geographic districts. The map is basically a filter, right? A curated lens between human perception and an infinitely complex environment. To achieve this slick interface, cartographers use a process called encoding. Encoding is essentially the graphical encryption of geospatial data. You can think of the cartographer as a systems engineer. They take a massive, messy dataset, say literally every tree, road, and elevation point in a national park, and they encrypt it into a highly organized visual sign system. Your job as the map reader is to decode it. And the entire goal of this encryption isn't to hide information, no way. It's to save space, highlight what's absolutely crucial, and make the real world digestible. All right, let's run a quick system initialization. Here is our roadmap for today's explainer. First, we'll cover the map as an interface. Then, Module 2 decodes the sign system. Module 3 gets into typography and labeling. Module 4 covers integrating data diagrams, and finally, Module 5 is all about mastering color systems. Okay, starting off with Module 1, the map as an interface and basic encoding. Before a map can show you the fastest route home or the population density of a country, it relies on a foundational visual code to kind of trick your brain into understanding spatial relationships. Enter Bertin's graphic variables. Once a cartographer decides to place a basic sign on a map, they can tweak these exact variables to encode vast amounts of data. They can change its size to show population volume. They can alter its shape to distinguish a church from a hospital. They can adjust the pattern, the direction, the lightness, or the color. So the crucial point is, these 6 variables are the absolute bedrock of cartographic encryption. Literally every map you've ever found intuitive uses these parameters flawlessly. Moving right along to Module 2, decoding the sign system. So now that we know the variables we can tweak, how do we actually assemble those raw data points into recognizable shapes? How do we build the buttons and icons of our cartographic user interface? Well, look at the flow of this schematic here. At the very top, we start with our basic graphical elements, a simple point, a line, and an area. That's our raw code. From there, we push those elements down into the graphical signs layer. Here, those basic geometries are compiled into actual map signs, like a little tree icon. They form text, they build different types of diagrams, whether that's column, pie, or Sankey, and they border images. And in the digital age, this layer also includes dynamic animations for temporal changes and interactive techniques, stuff like panning, zooming, and brushing, which links and highlights data on the fly. Finally, all of this combines at the bottom into the complete map graphics. It's a highly structured manufacturing process, really, taking simple geometry and turning it into deep associative meaning. All right. Module 3, typography and label placement. A map isn't much use without context, but injecting text into a dense spatial interface is notoriously difficult. If you've ever tried to read a super cluttered map, you know that poor label placement causes immediate system-level space conflicts. Let's play a little game of Spot the Glitch. Look at the lake and the street crossing on the left. When the label lake is placed right inside the geometry, it acts as a mask, completely cutting out a chunk of the map. While the lake shape is still kind of understandable, looking at the street crossing label, wow, it totally breaks the connection of the lines. It's a massive interface glitch. Now contrast that with the ideal placement rules shown on the right. For single-line labels associated with point signs, the absolute best practice is placing the text to the right and slightly higher than the sign. This ensures the reading order is preserved. You see the sign first, then the label, and absolutely nothing vital gets deleted from the map. Next up is Module 4, integrating complex data diagrams. So we've mapped physical things like lakes and roads, but how do we represent pure statistics that have no physical boundaries? How do we map flows and shifting quantities over time without completely cluttering our spatial UI? Enter the Sankey diagram. This graphic decrypts complex flows without relying on direct physical geography. What you are looking at is a visualization of quantity, in this specific case, emigration away from certain countries and immigration into others. The thickness of those flowing lines instantly communicates volume. You don't even need to see the actual physical borders of the countries involved. The diagram just strips away the geographical map entirely to prioritize the flow of the data itself. It's an incredibly powerful way to encode movement. Now, what's really interesting about this slide is how easily our perception can be hacked by bad diagram design. Look at these column charts. If you have two values, say $30,000 and $29,500, and your chart starts at a true 0 point, the columns look almost identical, which, yeah, is mathematically accurate. But look what happens when the cartographer shifts the 0 point to start at $27,000. Suddenly, the $30,000 column looks twice as big as the $29,500 one. It's a total visual distortion. Or look at the broken bars on the right. If you have one massive outlier value and you physically break the bar graphic just to save space, the viewer completely loses the proportional relationship to the smaller values. When reading data diagrams on maps, you have to be highly vigilant of these visual glitches. Finally, we have Module 5, Mastering Color Systems. How we actually display color fundamentally changes depending on whether we are projecting light into your eyes through a screen or absorbing light on a piece of printed paper. This is the classic battle of display technologies. On one side, we have RGB, red, green, blue. This is an additive system used for illuminating digital screens. Your phone or your monitor literally adds colored light together to create white. On the other side is CMYK, cyan, magenta, yellow, and key, which basically stands for black. This is a subtractive system used in print. Ink on paper absorbs or subtracts portions of white light. And by the way, the K is used for key because mixing cyan, magenta, and yellow ink in the real world doesn't give you pure black. It gives you a kind of muddy brown, so pure black ink has to be added. Cartographers have to rigorously manage the transformation between these color spaces, a process called gamut mapping, to ensure the map you see on your monitor looks identical when it's finally printed. Let's move to the next slide and see how this builds into actual map design. Once a color space is locked in, cartographers play with 3 core color variables: hue, saturation, and lightness. If a map is showing a sequence of data, like population density from low to high, the absolute best practice is to use a single hue sequential color scheme, rather than a divergent one, which you'd use for opposite extremes. For sequential, you pick one hue, like blue, and you simply change the lightness. A very light blue means low density, and a dark navy blue means high density. Why? Because it triggers an automatic psychological response in our brains called the dark is more bias. We instantly know darker means a higher value without even having to check the legend. Pretty cool, right? And that brings our entire visual interface together. We've stripped back the map from a simple picture to a highly engineered software stack. From Burton's graphic variables to the intricacies of typography placement, and from the flow of Sankey diagrams to the exact science of RGB versus CMYK. Cartography is entirely about graphical encryption. So next time you open your navigation app or look at a data map in the news, just pause for a second. Ask yourself, what is the data trying to make you see? And honestly, just as importantly, what is the cartographer deliberately left out to make that interface work? Thanks for joining this explainer, and keep questioning the interface.